the CAMBADA team in Portugal, in Aveiro specifically. And I'd like to start to thank Tech United for putting so much pressure upon us to bring our new platform to Andover this year. Without that, we wouldn't make it. But in fact, this new platform was actually finally assembled already in Andover. And so it was never tested before. It was tested during the competition, both the hardware and a new version of the software. So you have to imagine the level of faith we have in ourselves to do such a trick. And I would like also to say that in our team there are no mechanical engineers and no mechatronic engineers. We are all either electronic engineers or informatics engineers for computer engineering. And so I'd like to present basically the design that resulted in our new platform that we tested for the first time in Andover this year. It was 5 thrilling days of trying to evolve for the better. And in the end it was not so bad, I guess, because if we look at the results. The main objectives of designing this platform can be summarized as you see here. We used very inefficient omni-wheels bought from the United States, made of plastic. They degraded very fast. So we wanted to design efficient wheels, use and design a simple and modular structure. And as you will see, it's a sandwich slab structure that can make access to all components an easy task, and also integrate power monitoring and charging on the system. These were the main key issues that we wanted to address while designing this platform. As you will see also, of course, we borrow many ideas from other teams, namely Tech United, but not only. And that's why we are here. We are sharing ideas and evolve. So basically, some of the teams already use solutions like the ones we are using here. We have, I think, a slightly difference in the way that we use a more simple approach, I guess, than those that have been used today. Our rollers are based on aluminum roller with only 2 standard size O-rings. We don't use different size O-rings for the roller. There is a center steel sole, Teflon washers on the side, and 2 middle bearings over here that converge to this solution. And the wheel itself can be depicted here, and you see there are 3 main aluminum or hard aluminum pieces. That's the core one where all the rollers go on one side and the other. There is a total of 12 rollers on each side with an offset of 15 degrees between the left and right side. And this actually results in the same kind of deformation on the perfect circumference that I see from the wheels from, for instance, the Carpenauton or Tech United. This is really simple to assemble, unassemble, and maintain in that sense. So this is the final wheel. And we also decided, our previous platform, we have a direct drive. That means that the wheel was directly attached to the motor. There was no external support for that, for the wheel. And that poses a lot of stress on the roller bearings of on the motor itself. Basically, it was on the limit. And on the other side, there was no chance to adapt, apart from buying new motors. The top speed that we had in the previous platform, that was around 2 meters per second, and it was clear, at the moment at least, it was clearly too slow. So now we have a transmission through a synchronous pulley, which means that you can have different degrees of transformation. The basic sandwich, the base of the sandwich is made of hard aluminum, 6 millimeter thick, which is very simple to machine. And on top of this, the wheel support is a structure like this one, and as you can see, it is designed in a way that if you pull out these 2 pins, you can move the wheel very easily, even with sorry, I don't remember the name. The pulley, the belt, sorry, synchronous belt. So normally the wheel will be here, there is a synchronous belt attached, which is under stress, but because this is curved, we can very easily remove the wheel and put it on again. Okay, so it's an easy solution for that. So this is the whole set for a wheel on place on this side, and then we use maximum motors, of course, with a traction setup with adjustable weighted factor here. By changing these pulleys, we can use different torques versus maximum speeds, depending on exactly what we want. The base design is now roughly triangular, so similar to Tech United. The previous one was round, and the reason why we moved into this is because we want to use the sides to also play. So if you have a flat side, it means that you can make a pass bouncing on, for instance, another robot. With a circular solution, it's rather difficult to do that because it should be too much accurate to do a thing like that. So the traction final assembly is something like this. There is a hole in here, as you can see, and this hole is where we place our batteries. We have 3 little batteries. 2 of them are used for power systems, so basically for traction and for the kicker. And the other one is for the logic circuits. The power and logic circuits are fully independent. There is no ground connection between them. And if we want to exchange information, we use optocouplers for that purpose. Okay? This means that if something goes wrong on one side, the other side won't suffer from that. And normally, it goes wrong on the power side. It's a more common situation. Okay, of course, we also have fuses, and they are placed in here, but they are easily accessed from the bottom, as you can see. This is the battery's cover, and normally in normal situations we won't need to take this off because we can charge the batteries on the robot itself. So moving on to electronics, and on this side we are still using the same approach that we used in the previous platform. We use a distributed system interconnected by a CAN network, and all the electronics are designed and built by us. So we don't buy controllers, we don't buy any stuff apart from the laptop and apart from the components, of course. But the controllers are designed by us. Here you can see also home design battery cell monitor. Each of the batteries have 4 cells. And they have to be carefully monitored along the time because the voltage cannot go below 3.5 volts. Otherwise, you can recover it, but it's much harder to do it. So they are always or permanently monitored in here. Each of these monitors is monitoring one of the 4 batteries, and it has an audible alarm and also a blue light, a strong blue light, whenever one of the cells goes below the 3.5 volt limit. To end this part, on top of here you can see also home design battery charging control. This is responsible for charging the batteries in the robot without having to take them out, and is also responsible for using a CAN interconnection with these modules, also provide information about each of the cells to the laptop when the robot is on, the power of the robot is on. If you turn it off, then this only draws about 1 microamp, so you can stay there for nearly 1 year without wearing out the batteries. Okay, so the first level of the sandwich, you will see this is like an American sandwich with different levels. The first level of the sandwich closes here. This is only 6 centimeters high, okay, which means that most of the weight of the robot is near to the ground, which is also important for stability. And then the next level of the sandwich will bring, first of all, 3 rollers for ball support. This is common to most of the teams also. This is where the ball will engage when it's close to the robot. Each of these rollers also have a contactless magnetic absolute encoder, which means that you can measure either the position or the speed of the rotation of these rollers. And then we design a direct drive ball handler, so we don't have 90 degrees gear systems, and this is straightforward in this situation, based on an axis which has a small magnet on the top. I just put it here to show that, of course, we can also use one of these encoders. This is a 12-bit magnetic absolute encoder. That means that we can measure the absolute angle with a precision of 12 bit. It means something around 0.1 degrees or something like this. Okay. This magnetic encoder also has a microprocessor and a CAN interface, which means that I can connect as many encoders as I want using the CAN interface, CAN encoder. So the ball handling pair is now here, and of course there is also, seen from the back, two oil dampers that are used to damp the system while controlling the ball. This is one of the parts that have not been fully developed. Apart from that, the part of the control of these ball handlers, we just use a very straightforward bidding mechanism in Eindhoven, and we are now going to make this evolve in order to make it more effective. Another important component here is our kicking device. This is not as sophisticated as the one you saw from Tech United. Basically, this only allows single lob shots. The position of the pin on the ball is not adjustable in height, and it happens with Tech United, but it also allows for ground shots. And this is done with this simple mechanism. This is a servo in the back, and this servo will pull this to the side, and this lever is here for a single reason. It's that the plunger is actually in this solution is about 5 centimeters above the equator of the ball. And this is not good for floor shots because the ball tends to, if you shoot with too strongly, the ball tends to bounce. Okay? So this is slightly round, and the point of contact with the ball is around this point, which is exactly the equator. So with this solution, we can shoot the ball on the floor as we want. Okay, the end of this part of our sandwich ends with some electronics. This is the board responsible for inter-CAN gateway, because we actually have two CAN networks. One of the networks is only dedicated for the encoders, and this is also the responsible for the ball handler control. So the responsible for determining, based on position of these two systems, what is the ideal rotation speed of these two motors that we have here. With these motors, we can go up to 1500 RPMs tops, I guess. Here is a multi-layer interface. So basically, these are connectors that allow to interconnect the lower level of electronics to this level, and then to the top layer where the laptop stands. And this finally is CAN 2 USB. Actually, we are now developing a CAN 2 gigabit to be used next year in Brazil, hopefully, gateway, because what we have felt is that the USB connections are not reliable during shocks. And so from time to time we have failure due to that fact. And this is critical, since this is the gateway between the laptop and all the low level the hardware that's going behind. So we are developing a gigabit interface for that purpose. This is the kicker capacitor, and all the electronics is within this acrylic box, for protection, of course. We can also use 250 volts for our kicker. For the moment, we are limiting this voltage to 200 volts for precaution. There's no need, I think, to go above that for the current situation, I believe. And so now the sandwich is complete, as you can see. So now it's an American sandwich actually. And on the top, well, there are two switches there that are missing. Sorry for that. There are some status LEDs on here, and there is a micro LED display for the battery charge monitoring during battery charge procedure. And this is the look of the base of our system. This has been designed in terms of size to fit exactly within our suitcases to allow the robots to be transported with us, because it's much less expensive than dispatching them through the regular means. Okay, above this we have the structure for the vision system. So it's a tripod basically. Vision system stands over this ring, and it's something like this. This allows for an adjustment of around plus or minus 3 degrees in terms of rotation for accuracy and precision of the front angle of the camera. The support of the camera is designed to be height adjustable, so we can change lenses, or we may also change the type of mirror. Is one of the possibilities that we are considering now. And the structure is based on titanium bars. And this form or shape that is going out is designed so that the influence of these bars on the image is minimized, because as closer to the mirror these bars are, larger they will see in the image, they cover. Yeah. So this is to minimize that effect. So this is basically the complete set. Now we have the laptop over here. It is inside a carbon fiber box with internal rubber dumping, so that this can suffer from aggressive attacks from other things without suffering damage. As you can see also, this is placed above two small rails, and these rails will allow us to remove the lid of the box and then move it forward and open the lid of the laptop, like this, and it means that we can work directly on laptops without having to remove them from the robot itself. So afterwards, you just have to move it back, close the lid, put the top, and we're back on service. Okay, finally, of course, this is naked, poor thing, and we have to cover it up. So this is covered with a plastic material that has been molded to the robot, and it is the outside is basically a foam over which we have black carpet to make it completely black to the opponents, to help them to detect us. So that's the rules basically. So the robot must be basically black, and that's the reason for that. Okay, so the sandwich base, the tripod, this is the idea of transporting the robots with us. Means that we simply have to take the screws over here, take this structure out. These will fit within the suitcase, and there are a side on the suitcase that has space for that, for the head with the camera and the laptop. So of course will go with us on a different suitcase. So ready to go. This was the idea. We made it all in a very short time. It was actually a hurry. We assembled it in Eindhoven, and after 5 days we managed to got third place. It was actually very thrilling. Of course, we brought home pages and pages of I call it bugs.
Future improvements.
Yes, future improvements. Reasons for future improvements, of course. And so we are hoping that with this solution, next year Brazil will be actually playing a little bit better than this year, and playing at top level. Let's see. So I'm hoping for that. So if you have any questions regarding this is a very simple and straight presentation. As you can see, the major ideas are quite clear, I think.
Basic, separate the computer and the cells. It's less than 32 kilos.
It's less than 32 kilos, yes.
Okay.
Yes.
So if you dismount the top, you can put the whole system in one suitcase.
Yes. It was basically we started. Well, it's not true. We started the design without those concerns. At a certain point in time, especially after going to Mexico, because we had to bring the robots with us, we restarted the design by measuring exactly the suitcases and see exactly how we can do it to fit them in the suitcase. Okay, so the measures of this structure, basically, which is the worst in this case, because these three arms can come apart, and then it's just like this, and it is designed to fit the suitcase. So it's up the transportation of the robots. Yeah.
What makes you choose for the CAD interface as an interface?
Historical reasons, basically, because we are in a department where we do a lot of instrumentation, and we have a lot of experience using different network buses for embedded systems, and we have a lot of work done upon CAN. So we have special protocols, synchronous protocols, for instance, over CAN. Okay, and so we have a lot of experience with that. It's quite reliable. It allows high throughput, at least for the type of bus we are using it for real time for this solution, and it's actually a good solution for us. It has been proved as to be quite reliable.
Because you use it already from the start.
Yeah, basically, yes. The only weak point actually is the gateway to USB because of the USB connector.
It's only the connector.
Yes,
so
only
you
the connector.
could not in a way make it so tight.
Yeah, we already discussed opening the laptops and soldering it inside and stuff like that, but I don't think that's a solution. So that's why we're going to gigabit connection, Ethernet connection, yes, because that has no problems. That one has no problem.
With USB, I heard also that there can be electrical problems.
Yeah.
The controller may reset because if it gets some pulse control on the line and it's...
Yeah, that's right. Normally we don't experience that kind of problems, but when we have problems, normally it has to do with crashes between robots. So there are a lot of vibration, and that's what makes the system to collapse in that those situations. With Ethernet, for instance, our camera, it has a gigabit Ethernet connection, never failed. So I think changing to the Ethernet will be the solution for solving the problem. And that's why we design this. Yes.
This is an open design in the sense that others could reuse it and rebuild it themselves.
Okay, I guess this will be placed on the site of this workshop for starters, and I think yes, of course, it is open design.
So would it be?
So I think we could, if you we could discuss that, but we could put the base designs of all the hardware, for instance, on your platform for software and hardware, and also the electronics.
So that would be great, I think, if you could add it to the RoboCup platform site.
Yes, we have discussed that already, and I think we should do that. And not only with the hardware, but also with the electronic hardware.
Yeah, sure.
Yes,
That-
of course. Controllers
Not only
and
the
everything
mechanics,
else.
but also
Yes.
the electronics. So if you can put all the drawings and documentation on it, it would be great. What's the total cost of the bill of material, the cost to make it manufactured?
That's a good question for which I don't have actually an answer. And that's simple why I don't have an
The
answer.
important thing is this is less than 5,000 euros.
No, I don't think it's less than 5,000 euros. And the reason why I don't know exactly how much it would cost is very simple. Because nowadays in Portugal, the only way to get them sponsoring is through materials or services, no money. Okay? So, for instance, let me go maybe to the beginning or something. For the wheels, for instance, we had a company that machines all the rollers for us, and they were for free for us. So I don't know what would be the cost of that. And Also, most of the work that is here has been done in one of our mechanical workshops, okay? And it has been done by me. So I don't know how to account for that cost. Okay. So basically, I designed all the hardware of the platform, and I've worked with the CNCs, machining all these parts, and assembling them, and etc., etc. So I don't know how to account for that. So in terms, also from the electronic side, I think it's much less expensive to develop electronics the way we do than to buy direct controllers from any company. Okay, we have a lot of experience doing that. They are reliable, they have been tested for several years now. We have been involved in them. So I don't have a number to give you, but I don't think it would be below the 5K.
Especially also the milling of all the plates cost a lot of time. That was one of the reasons that we replaced that by a simple plate, metal plate, to perform in much less number of operations during manufacturing.
Yeah, that was also the idea at the beginning, to make it simple,
Yeah.
not complicated stuff.
It looks, I mean, it's a single plate, but it's not so simple to let a machine manufacture it.
If you want to use a CNC, no, but in this case, probably you could use a laser cut machine or something like that. Because this is basically only straight cuts.
Okay.
In that sense. We didn't use a laser cut machine, we used a CNC, but you could use a laser cut machine for that.
But why the solution of ball handling? You didn't angle the wheels. Is that cheaper or what's the idea?
It's much cheaper,
Yes.
first of all.
Okay.
Okay, these motors that we are using cost, I don't know, 35 euro.
Mm-hmm.
Okay.
But you can dribble with it. You also then think you can dribble with the ball.
Yes.
Do you have experience with this system? You can't grab the ball, that's one of the problems.
We can't grab the ball.
Not if you're only touching one of the wheels.
Yes. Because okay, the design is different from the ones some of the teams use. There are two approaches basically.
So I think your question is whether you can grasp the ball with the small omni wheels.
Yeah, that's
the
The
and
small.
did you compare them
The
to
top wheels.
normal wheels?
The top wheels.
Yes.
Yes, okay. Because of the size of the wheels.
No, they are not angled.
This,
Yes.
okay. This basically rotates, if you want to grab the ball, the angle is maybe 90 degrees offset from the angle that you use. But other teams also use this kind of angle, okay? So if the ball touches this rotates on this direction and pushes the ball against this one. Okay?
Okay.
And so depending on the position of the tool grabbers, you can adjust the speed so that you push this one and then this push this one inside. It's a certain angle, they stop simply and grab the ball. One problem we have at this moment, and
You can keep them in the reference position without continuously spinning the wheels.
yeah, that's right. And we can of course dribble backwards, forwards, around. We have done that already. We still have a problem that has to do also with the problem you are dealing with. That this starting angle is too low for the moment. We have already decided we have to make it higher, because at this point, if the ball comes too fast, it will simply bounce back because of the energy. But if it is higher, then you can actually touch it higher on the ball and bring it in.
Because you also have temperance on it, right? So
Yeah.
the energy of the ball is.
That's right. That's right, because of the damper. So we, at this moment, we actually have a movement of about 13 degrees, I guess. It's too much. There's no need for it. I think from the bottom position to the top position, we have 13 degrees. And we don't need too much clearly. So, but there's something to evolve and to see what's the best solution. Apart from that, this works nicely. We have to work on the one aspect which is very important is this is stiffly attached to this base, and this is a problem. This year in Eindhoven, one of the water robots crashed at top speed from the side on this, and it simply broke this axle. Okay. So we have to have a system for damping these situations to absorb the energy. Otherwise, this is the only situation which is actually critical here. But we have to dump that.
You could also retract that in a way.
Yeah, but for that we have to have some sort of active system. That means more power, more energy, more motors, or whatever. Okay. Of course, we can do that, but we are trying to avoid those situations. At least one of the things that I would like to discuss when we come to the rules is the energy issue. We should think about making robots with a maximum allowable energy level during a game, like humans. If you shoot too much, then by half of the game you are dead. Or if you run too much for too long, then you are dead.
That is already the case.
Sorry?
That is the case already, because you have batteries.
Yeah, that's right. But you don't have a way to level teams, in that sense. Okay? And the idea is to give all the teams the same level of energy, so that no one has advantage over the other. Okay? You can put extra batteries if you want to, or make it lighter, or whatever. Okay? But what happens with us, of course, if we run too much, then we eventually have to come out of the game earlier. Okay? In these situations, with this robot, with our set of batteries, we can play one day, we can play 4 games without changing or recharging batteries, which is too long.
What is the capacity then?
The batteries, I guess they are 5.7 ampere hour.
Each.
The voltage.
And voltage, they are 4 cells, which means for power will be around 35 volts, and for the logic part will be around 16 volts, something like that. Because for the power, it's a series of two batteries.
4 cells? You using 4 cells?
4 cells, yeah, in each battery. For, the nominal voltage is 3.7, but normally they charge at 4.2, so you come down from 4.2 to 3.5 is the minimum. So if you have an average of 4 volts, it's 16 volts for the logic, 32 volts for the power side.
And during the game you are balancing?
No, we're not balancing. No, there's no need for that, because there's plenty of energy on both sides.
But during
We actually, for logic, for instance, we have a DC-DC converter for around 6 volt, because it makes no sense to bring 16 volt to a chip that has components working at 5 or 3.3 volts. Okay? Makes no sense.
How's the electrical connection between these two layers?
The electric connection is done through this. Well, there are no details, of course, but I can give the details later. Through this board, okay? You see this opening? There's another one on the bottom, and basically these are electrical connectors with a set of cables that go to down and connect down. There's another one that goes up. Okay?
You have to
So it's just unplug.
You have to unplug them if you want to separate the two.
Yeah, it's a single. It's quite simple actually. It's just yeah. If you remove the cover, it's directly accessible. This is this high, so it's very simple to do.
So why do you put the laptop on top of it? Because you say I have to buffer it and all that kind of things, and my feeling is always that it is so fragile.
You suggest to put it inside. Okay, there are several problems. One has to do with temperature of laptop. Okay, on top, of course, that box that you see there. Sorry, okay. This box has a lot of drills.
Okay.
Okay, both on the bottom and on the top, and on the side. And so we have tested this year. It's okay because the laptops never get too hot. Okay? So this is a good solution. On the other side, this has been designed so that the ball actually never touches this box, because it will touch this tripod before touching the box. Okay? The position of the box inside is completely protected. The ball never touches it. So the only problem has to do with crashes between robots. Yeah. And so inside is dumping made with soft rubber, and the laptop is inside that soft rubber.
Okay. And you are not depending on the function of the hard disk? Because it's only logging.
Well, no, because in our present situation we don't have hard disks, mechanical hard disks. But on our previous platforms we have mechanical hard disks since 2007,
Yeah.
and we never had a single problem.
Okay.
Never. Most of the time it's stopped. Because you don't want to access the hard disk to play, you are running processes.
Yeah.
Okay, so the disk is stopped. Yeah.
So the tripod doesn't seem to be very stiff. Aren't you afraid?
This one?
Yeah, for small deviations with respect to the camera position and.
Yeah, okay, this is done with 3 mm steel, banded
Especially on the donations.
here.
Yeah.
We didn't have any problems on
Do you
that.
lift it by grabbing the tripod? Or?
No, no, and that's another problem we still have to solve, is to get some sort of solution to lift it from behind, from below, sorry.
So are you automatically compensating for any skews in the camera position with respect to the base platform?
Well, as long as this screw in here doesn't move, the tripod wouldn't move unless one of
Well, that can be hit by
banded. Huh?
could be hit by a ball, for instance.
Yes, that's not a problem.
Does that also hold for the other two bars? The
This
position of
one.
the mirror with respect to the camera?
Yeah, this actually are 4 bars, not 2. And they are reinforced in these small pieces here, on top and bottom, to make it quite stiff. Okay. This is a problem we had on our previous solution. First, because the bars were in steel, they didn't have this kind of reinforcement. And when we got a ball struck by a thing, for instance, normally it would get like this.
So now you have four bars in the way of the camera.
Yeah,
but
but
did you consider the
no,
transparent tube?
no, because they are farther from the mirror, which means that they are slimmer on the image. So it's not an issue also. Okay. Of course, we could use a solution like you, with like your solution, like glass or something. But this works fine. Yeah.
Does the laptop has its own battery?
Yes.
And how long does it last?
How long does it last?
2 hours, maybe.
2 hours. Yeah.
1
Okay.
hour and a half, 2 hours.
Yeah.
When
Okay. The system that powers and charges the batteries also charges the battery of the laptop.
Oh, okay.
Okay. 2 hours is good enough. So, yeah,
How do you build
I
this?
would expect so many questions about this.
How do you build your mirror?
Our
Your mirror?
mirror, no, we didn't. We bought it. Actually, we bought it back in 2006, I think. 2007, maybe. 2007. Yeah. And one of the things we are considering now is to build new ones. With a different design. Because this design, we bought this from Fraunhofer, yes, Fraunhofer Institute. And this is an hyperbolic mirror, and clearly it's not the best possible solution in terms of cover distance versus resolution. The problem is that you get a lot of resolution close to the robot, but it decreases at high speed at higher distances. So with a different equation for the mirror, we can balance that a little bit more. You will all the time will have that problem. The farther you look, the lower is the resolution. But it's, I don't know, 7 meters away, 1 pixel will be something like 20 centimeters or something. Yeah. With a different design, you can reduce the resolution closer to the robot and compensate for the higher distances. so that you can bounce a little bit. And we are redesigning this too. I don't know if we'll have money for making that, but let's see.
Are you also thinking of adding a Kinect sensor?
Yeah, we already made a lot. I've made a lot of some trials with Kinects. Basically, the Kinect is interesting for the goalkeeper, but the Kinect still has a lot of limitations, namely the range, the minimum range and maximum range. So it's probably not a good solution. I don't know if the solution with the FPGA that has been presented today would not be a better solution for the moment, at least. The Kinect is nice. We can actually follow the ball in 3D during a certain interval. But if the ball flies too fast, probably we won't be there on time.
Yeah.
Okay. So we have been making some trials with Kinect, but I have some mixed feelings about the development on this kind of robots. So I'd like to extend this too much. So next one. Thanks so much for your questions.